Okay, thank you everybody for coming. I hope you had a great time at the summit. This is one of the final sessions. Thank you for making it here. We're gonna be talking about implementing a routing pattern, a routing agent, leveraging an open source library called DSPy in a Databricks platform. So a little bit about me. I'm a staff data scientist at the ML practice team in the professional services unit of Databricks. And about a year and a half ago, I stumbled into DSPy. I was implementing a text-to-SQL project, and I couldn't make it to have any better accuracy. So I read about this package that will give me some optimizers that I could then apply. And it not only allowed me to improve the accuracy, but also gave me a very, very nice abstraction, a very nice way of seeing the problem and prompting that I have used ever since. So I find it very powerful, and I'd like to share it with you today to give you an idea of what I mean by that. Is prompting has an inherent problem, what I call the big wall of text. You start with a very simple task, very essential task, and it tends to work okay at the beginning. So this is a classification, a sentiment classification. And a very simple phrase will do at the beginning. But then, you crash with reality and you start seeing examples that don't quite work. And you start looking at tricks and you apply role play, you apply background and context, and you better detail instructions, and you better define your categories, you give it analysis. You start using all the tricks that you have in your bag. And every day, more and more tricks are kind of discovered. And these tricks may be good for one language model, but not for another one. And very soon, you see that your very simple, very essential task becomes this big wall of text. And the main problem you have is that in this big wall of text, you have conflated all different concerns. You have all these tricks that are basically just this accidental complexity that you added to make your prompt better and to get better quality on your results. But this is a kind of a greedy optimization that you did based on the data that you have at the moment in an ad hoc fashion. Maintaining this is a nightmare. If you have to change the essential task, now you have to start basically from scratch. It's not very good for the long term. So we have been doing this for 2 years or so. Gen AI has been the kind of more common in the last 2 years. So now we're starting to see the pains of maintaining this type of systems. And the abstraction that DSPy provides you help us with this problem. It's a very simple abstraction. You start with a signature, which is kind of a structure prompt. And this class, Python class that inherited from DSPy signature, has an instruction. It's your doc string, and you're telling it what to do, what's your main concern. And then you define your inputs. And by the way, you can type them, type inputs. You can also give them descriptions in the input field. You can find the description. And then you define your outputs. And it's very handy. As you can see, I can define my output with the type literal with the predefined emotions that I want to classify. So this is exactly the same that I showed you before with the very succinct sentence, but in a programmatic way. And now you have defined in an structured way your main intention. And because this is structure, DSPy can start exploring, changing different things, and optimizing it. So it could alter just the instruction. It could put more emphasis on extracting the types. It could give few short examples. It could do many things because it's not just a blob. Now it has some structure. But it's very intuitive for you to apply this structure in your prompts. So it's not a big lift to move towards DSPy. Besides defining the signature, you also define your kind of prediction strategy, which in DSPy is called a module. And DSPy offers you, out of the box, several strategies. You have the predict, which is the essential one, the simplest one. It's just a prediction. You have chain of thought, you have React and others. And you can create your own modules by composing these out-of-the-box modules. And then finally, you define your language model, which if you're using Databricks, is very simple. You just point into the foundation models, and that's it. That's all you need to do a DSPy program. And the beautiful thing is that you can change any of these abstractions independently of the other abstractions. So your signature could remain the same, and you can change your prediction strategy to be a chain of thought or a React a strategy. You can use a different language model. And DSPy is actually under the hood using what is called an adapter to unfold the signature and actually render the prompt that will be sent to the language model, looking at the language model and selecting the adapter that will be most appropriate for that language model. So it allows you to plug and play different things and iterate your POC towards production very, very easily. And it's very simple and intuitive. You don't need any other constructs. It's also very free. It doesn't impose to you like an order or a DSL that you need to follow, a domain-specific language or a pipeline that you need to follow. It's just Python. It almost feels like you're using helper functions in your Python. So that's all you have. And at the end, you have your classifier, you pass it, and that's all you have. So with this in mind, I'm going to spend the rest of the session talking about this pattern I have been implemented with several clients, leveraging DSPy to route requests. And the problem I'm trying to solve with this pattern is clients have been, again, implementing in the last 2 years or so many AI assistants, many AI solutions, but they tend to be dispersed. So different endpoints, different user interfaces, and users are starting to get lost. They don't know where to find which assistant. Governance is all fragmented. If we could just add a single point of entry, a place where everybody is sent, and that entry point will know which AI solution should be called, depending on the request, then that will allow you to have a consolidated governance, and it will make the life of the users easier. Therefore, the adoption will be better. So this is the problem that we're trying to solve. Now, if you close your eyes, squeeze your eyes, this will probably smell to you like React. This is like an agent, it's reasoning and acting, and you will be right. This is where I started. DSPy has a module, as I mentioned, that is React, which basically does a reasoning phase that selects the tool and extracts parameters from the request. Okay, selects a tool that seems to be the best one for answering the request, and then extracts the parameters that the tool needs out of the request, then acts by executing the tool, and then finally reasons again to say, okay, do I have enough information now to answer the question or to answer the request? If the answer is yes, then it renders the response. But if the answer is no, then it loops again, and it starts selecting another tool, extracting parameters, running it, and keeps doing this until it has enough information to answer the request. So this is very, very similar to what we need, but it's actually a bit more complex than what we need. We can simplify it, because if you see in the router, we don't have a sequence of steps. We have just one step. We need to select which of the available tools is the one that we want. So I've taken the module that comes in then DSPy. It's open source. You can see it. You can modify it. And I created then this router pattern, which is just a simplification that only does a single reasoning step, selects the tool, extracts the parameters, then it calls the tool, and finally, it gives you either the response out of the tool, or if there is an error, which tends to be particularly in the parameter extraction part, then it focuses on just extracting the parameter and solving that problem. So it will skip selecting a tool. It will just focus on better extracting the parameters. Okay, now, in order for this pattern to be effective, there's some fundamental aspects that we need to cover. No? It has to have high accuracy. It doesn't matter how good is the tool or the AI solution that is being called. If the router sends it to the wrong one, then everything will be bad after that. You want to be able to scale it. You want to be able to have tens of tools or hundreds of tools. And you want to be able to have stateful interactions. So it could be that the tool needs more information to proceed. You're asking, where is the best pizza place in the city? And the correct tool is selected, the pizza place recommended, but the tool needs to know where you're located. So it asks back to the user, hey, where you're located. You could think then having the tool as a state machine that transitions to a state of requesting information, and when the user sends information, you don't need to go through the process of selecting the tool and extracting parameters again. You know this tool is in this state, is in an intermediate state, you can jump all that and go and then continue from there. Okay. So for the high accuracy portion, we leverage the DSPy optimizations. Particularly a new one that was unveiled yesterday, which is Simba. I won't go in details on Simba, but at a high level, I can tell you that it uses mini batches. So you give it many examples, and it will sample the examples and apply alterations to the instructions, the future examples. It will try many things and select the changes that provide back a bigger impact, a bigger incremental impact. So those changes are selected, and then it samples another mini batch and keeps applying that approach until it either reaches the max number of iterations that you give it, or the improvements are below a threshold that you set up. Okay? Now, what's really important in this case is how you measure improvement. The good news is that in the case of the router, it's kind of simple, because if you can set up the questions ahead of time, you know which tool should be called, and you can know which parameters should be extracted. So you can set up those expectations ahead of time, like I'm doing here. I have a list of dictionaries with the question, and I know that for that question, the tool call should be the tickets tool, and the argument should be this one with this value. Then it's very easy to create an evaluation function, a metric, that receives the example and the prediction and just compares them. So it will be true if the tool and the name of the tool and the parameters are the expected ones. It will be false if not. The way then you use DSPy is very simple. You transform your list of dictionaries into a DSPy example, and instantiate Simba, passing the evaluation function, telling it how many iterations it should take, and what's the max number of future examples or demonstrations that you want to add. Then you call the compile, and that will do the optimization. And this is a step that you do ahead of time. This is a step that you do before you deploy the model. This is not a step that you do on runtime. The compiler will run for some time and then give you an optimized agent. And that optimized agent, that optimized model, is the one that you will then register in deploy. On the scalability side, what we can do is we can rank the tools based on the question. So we could leverage vector search, Databricks vector search, to see which tools are more likely to be useful based on the semantic similarity to the question. So this won't select the tool per se, but it will allow you to diminish the number of tools that you're passing to the router, therefore making the prompt a lot smaller. Vector search is very fast, so it would be milliseconds, and by making the prompt or the context window much smaller, it would be less costly, and it would be faster. Vector search is built to handle billions of records, so you have a lot of room to add tools when you apply this approach. The code is very simple. If you're familiar with the vector search client, you just instantiate it and use it to retrieve the top-end tools based on similarity search, and then that's what you pass to the router. Now, there is a step you need to take ahead of time. You need to create a table that has all the tools, the descriptions of the tools, examples for the tools, and have a column that has all these combined, and you index that column. Again, as I mentioned, vector search is built for billions of records, so if you have tens of records or hundreds of records, that's little data. Processing this pre-step takes minutes. It's very fast, but you do need to do it. So. On the stateful side, this is one, I'm gonna give you a bit of a polemic approach and one that I feel is more elegant. But the polemic one, for me, has been very useful and very convenient, so I'm gonna share it with you. Many of the consumers of the routers will be UI systems. They already handle session state. So you can pass back and forth the state to the consumer. And this way, you can keep the router stateless. The benefit of having the router stateless is then that now you can replicate it and you can scale very easily. You can pass the state in the custom outputs and receive the state in the custom inputs of the chat model and the chat agent MLflow Python classes. Now, this is convenient, but it's not as elegant and it has some drawbacks, which are the following. You are actually coupling the router with the consumer. Now, the consumer needs to know a little bit about the internal processings of the routers, which is not good. It's kind of a smell. It's convenient. I have used it. I'm guilty. I have used it. But use it, be careful when you use it. Also, you're adding more traffic, network traffic. So the state has to be like really, really small. To give you an example, going back to that example that I mentioned of where's the best pizza place, the tool will say, well, in which city are you located? And it will send back that custom output with the state that has the tool and the tool state. And then the UI, when sending back the answer of the user, will then send back the state as is, the same state in the custom input. And then the router will know to not select a new tool, but keep using that tool in the state that it was before. Now, you can do all that in a much better way using Lakebase. Now, caveat, Lakebase is really new. It was unveiled yesterday, but it will be a much better approach. It is built for scalability, low latency for both storage and retrieval. It's a managed solution, so it's a lot simpler to implement it. You have no coupling, no logical coupling between the service, the router, and the consumer, the client. And it's all open source based technology. So I would highly recommend you can use a very similar approach of storing the state, the very same state, but instead of passing it back and forth, you could use Lakebase for that. So some of the lessons learned by implementing this pattern with customers. First, premature optimizations are the cause of many headaches. I wouldn't start with the DSPy optimization right away. You can get very far by just using DSPy at the beginning, just staging it, using your signature, making everything very, very clean, and you get very good accuracy. You set up your metric, your evaluation function, you can use all that. And only when you have critical mass, when you have enough tools, when you have also enough representative data, then you can start using the optimizers. It's very important to have a really good delineation of the responsibilities. If you have tools that the description overlaps semantically, the language model will get confused. And it will select one or the other, depending. So you need to spend some good time, and this is non-trivial when you start having many, many, many tools. So it's very, very important to delineate the responsibilities very well. And then finally, for tracing and troubleshooting, ML flow traces is your friend. It's really good, really powerful. If you put that line of code that I have there, mlflow.dspy.autolog, you got full logging of all the traces of everything that's happening in DSPy. And you can see how DSPy is transforming the signature into the prompt that is actually sent to the language model, what the language model is sending back, how it's parsing it out, how it's calling the tool, and everything is set up here in a very nice user interface. And by the way, if you're using model serving this and you activate DSPy autolog, this will go to the inference table so you can see what happened in production later on. So this is very, very powerful. Well, in conclusion, I hope that I make you curious about DSPy. DSPy 3 was unveiled yesterday. It's production ready. This pattern that I'm showing you, I have used in production. We have clients using them right now in production, and we have volume tested, and so we're using thousands of users using the pattern. I hope you find of interest the router pattern, and you see this the problem that it helps solving, and how it's a modular, scalable approach for solving that model. And stating a little bit the obvious, Databricks is a very good platform for implementing these type of systems because it gives you out-of-the-box governance and monitoring and much of what you need. Okay. So with that in mind, I think I have about 2 minutes or so for any questions that you may have.